Thank you very much, and thank you for, thanks to the organizers for inviting me. Title I sent to the webpage when I first was thinking about presenting is kind of misleading because I said I would speak about gauge theories on algebroids. Rather, I will restrict to E-manifolds and do some comments on algebroids in the end, and you'll see why. And this is, of course, joint work with Pau and Eva Miranda. And this has been most of the content of my bachelor thesis. So first of all, I am really sorry because this topic or this talk will be almost trivial for most of you. So I will try to compensate that through a pedagogical point of view. And I will start explaining what are classical gauge theories, but from the eyes of a physicist. Then I will explain what are E-manifolds and really basic notions about their geometry, specifically differential geometry. And then I will speak about preliminary notions for speaking about gauge theories on these manifolds, the main results, which are gauge theories, and some applications to physical problems. So things I will assume that everyone here is, of course, familiar with symplectic geometry, smooth symplectic geometry, and that whenever we have a Riemannian manifold or a pseudo-Riemannian manifold, the equations for the geodesic become in the cotangent bundle identified with the tangent under the musical isomorphism, they become Hamiltonian, and the kinetic energy is the Hamiltonian generator for this flow. So now I want, in all of this description, we consider a manifold. Generally, in general relativity, we consider a four-dimensional manifold, which we call the configuration space, and we assume that the physics are completely described by these configuration variables. But I want to say that it doesn't really have to be this way. So for instance, if I draw two spheres here, and I ask you, which is the charge, the electric charge? Can anybody answer? Well, probably not, unless I impose some external electric field and see the response. This has no response. This has a certain acceleration. So this one is charged. This one isn't. This is a toy example to illustrate the fact that for some physical theories, we might be lacking information just describing points in space-time. We might lose information about electric charge or color charges and other stuff. So gauge theories introduce this kind of behavior by saying, well, to each point in our space-time, in our base manifold M, we can attach a manifold of symmetries, which in the case of electric charges would be a line bundle and so on. And these will become our configuration space. So we start with a very easy definition of fiber bundle, but from the eyes of a physicist, this is like an extended configuration space. And now we can consider equivalencies, which are represented by the gauge group. In the gauge group is a subgroup of the group of diffeomorphisms of the bundle. And we are requiring basically that the underlying physics, the observable physics in space-time remain unchanged by these transformations. So now we're ready to speak about what gauge theories are. A gauge theory is a fiber bundle, which we understand like an extended configuration space, together with a G structure. And I assume that the notion of G structure is familiar to most of you. So now we have spoken about configuration spaces. What about the fields? What about the equations of motion? The fields, similarly to how we do in classical mechanics on the tangent, or yeah. Could be, but doesn't have to, really. A G. Yes, I mean, you can define the idea of a G structure can be defined for arbitrary fiber bundles. Now, about the physics, I really have not thought about the physics. Maybe you could argue that you have some kind of reduction or identification. Yeah, like you have a G action on the fibers which factors through left or right translations on the group. You have kind of a representation. Oh, sorry, I didn't know. I'm taking this one. Yeah. Doesn't have to be. Yeah, could be a manifold. And normally in the literature, they are not introduced as vector bundles. And I think you can lose some generality in that regard. And you can, the theory works for fiber bundles. A representation, yeah, representation of some group. Okay, thank you. Okay, thank you, thank you. I didn't know. So about the gauge field, classical mechanics, we take a connection, an affine connection on the tangent bundle, and now we replicate this and define gauge field to be G invariant Ehresmann connections on some fiber bundle. And this is the classical picture, and we identify them as splittings of the Atiyah sequence. And this is very important. We have a splitting lemma, and this is the key result during all of the proofs, which I will not do, is basically use splittings of the Atiyah sequence. And this result is not really obvious. You have this result on every abelian category, but vector bundles are not an abelian category. They may fail to have kernels. In any case, you can write down some normal coordinates and prove the splitting lemma by hand. So in the end, splitting lemma is satisfied. That is all we care about. And now, why do we always find a formulation of gauge theories over principal bundles instead of fiber bundles? Is it because the symmetries of particles are actually belong to Lie groups? The answer is that it doesn't really work that way. It is because principal bundles are like universal models for fiber bundles with G structures under my language. And we have this theorem here, which is, you can find it in any classical geometry, differential geometry book, which tells you how to construct a fiber bundle with G structure starting from a principal bundle. And this is the associated bundle construction. And same happens with connections. You can induce a gauge field from a principal gauge field or a gauge field on a principal bundle. And now I have said something about configuration spaces. I have said something about fields, which somehow should imply something about equations of motion. So how does this work? And the very first like hands down solution for the problem was given by Alan Weinstein in 78, I believe. Well, before that, people had already written down what are Wong's equations of motion in coordinates for a particle under the kinetic energy as a Hamiltonian for the system. But it was Alan Weinstein who showed that there exists a symplectic formulation, like a universal phase-phase formulation for Wong's equation. And the basic idea is you have like a fiber bundle, you have your base manifold, and now you take this to be like a sort of extended configuration space. But we know that mechanics are written, at least on the Hamiltonian version, on the phase space. So now we have the phase space, classical phase space, and we would expect to have equations of motion on the extended phase space. But now we have the tangent map, we dualize it, we obtain a map here. If we have a Hamiltonian here, how do we choose a Hamiltonian here? And the role of the connection comes here as a horizontal field. A horizontal field is, well, horizontal lift is a section So now I dualize it. It becomes a retraction. So now I can define a Hamiltonian here. This is symplectic. This is symplectic. This defines some Hamiltonian equations of motion, which are Wong's equations of motion. But the picture doesn't really stop here, because as we are defining splittings to be G invariant, and we have a cotangent lift of the group action here, we can actually take Marsden-Weinstein reduced phase as the natural phase space for the equations of motion. So this is the big picture about Wong's equations of motion. And the next piece of work was done by Montgomery, who showed that for the case of Yang-Mills theories, where now we have as a fiber, as the fiber of a fiber bundle, we have a Lie algebra, and we can understand that it comes associated to a principal bundle, the natural associated bundle. That is the framework for Yang-Mills theories. Then these spaces of Weinstein can be regarded as symplectic leaves of a bigger Poisson space. And this was his contribution. And there was an earlier paper by Stenberg about something which is called minimal coupling in physics, in which you modify the symplectic structure here. You change this way of connecting universal phase spaces, choosing a connection to a universal projection, but instead, you now modify the symplectic structure here. And the thing is that these spaces are symplectomorphic. So Weinstein generalized his proof for universal phase spaces. And Montgomery also generalized Stenberg's minimal coupling to Poisson manifolds. So now, we are interested in the case where our base manifold, like spacetime, has some kind of singularities. We are interested in describing an extension of classical gauge and Yang-Mills theories for these phases. And this is where I introduced the class of manifolds to be studied, which are E-manifolds. Sadly, E doesn't come from Eva Miranda. E comes from E. An E-manifold is a smooth manifold with an involutive and locally free C-infinity submodule of vector fields. And we understand these vector fields to be the only true representatives of the motion of our physical system in the base space. This is a technical lemma, which uses Serre-Swan's theorem, which we have already heard sometimes during these talks. Because we have locally free infinity submodule, we can regard it as the set of sections of some vector bundle, which is called the E-tangent bundle. And basically, you can reduce the Lie bracket of vector fields by involutiveness to this submodule. You can define locally an equivalence of sections and elements of E. And there is a kind of non-trivial, but also trivial result, which is that the anchor is generically injective. And this subtlety will come into play when we define lifts of diffeomorphisms. So now, how did we come to this story? It all started with Melrose, with the B-calculus of Melrose in his attempt, or in his proof, his generalization of the Atiyah-Patodi-Singer index theorem for manifolds with boundary. And then Richard Nest started studying like the formation, quantization of Lie algebroids, which generalize all of E-manifolds and B-manifolds and all of this stuff. And the symplectic geometry of B-manifolds was extensively studied by Victor Guillemin and Eva Miranda. And recently, the differential geometry of E-manifolds was investigated by Eva Miranda and Jeff Scott. And Eva Miranda and Richard Nest have really interesting results concerning E-manifolds, which we'll be able to see at the Big Poisson event. So looking forward to that. Some examples of E-manifolds. Of course, B-manifolds. When you have a B-manifold, you can identify the E structure to be the set of vector fields tangent to an embedded hypersurface. When we have C-manifolds, which are manifolds with not an embedded, but an immersed hypersurface with self-transverse intersections. We also have some local normal forms, and we can check that locally this is an E structure. More generally, foliated manifolds, regularly foliated manifolds, are examples of E-manifolds by Frobenius' theorem. And some examples arising from physics are level sets of a Hamiltonian. For the case of general relativity, we have proper time foliation, which is just foliating a subset of the tangent bundle by vectors with same norm. And this is regular, provided you eliminate points with zero norm. And this also works in general if you define a foliation by preimage of regular level sets of Hamiltonians. You also have regular foliation, and it is an example of an E-manifolds. And actually, dynamics are restricted to these hypersurfaces. And another instance where some structures related to E-manifolds appear is Shamar-Lerman certifications, in which we drop the freeness condition of a group action. Shamar-Lerman proved that the quotient has a natural symplectic stratified structure. So on to the preliminaries for our main goal, which are gauge theories. If I learned something at Madrid, generalized complex geometry interaction, is that proofs besides commutative diagrams are actually recipes. So if we have a proof, which is a recipe, and we want to generalize it to other contexts, the only sensible thing to do is to write down a shopping list. So I have done my homework. I have here my shopping list. So now let's check that everything is actually in store. First of all, pullback structures. When we have a base manifold with an E structure, we can actually pull it back to any fiber bundle by surjectivity of the projection and obtain an E structure at the top, which is actually the pullback algebroid of the E tangent bundle. Or if you want to describe it in terms of local sections, you can take the preimage of the E structure, consider the span of these E structures, and they are equivalent vector bundle or Lie algebroid structures. And basically, it comes from the fact that we have some natural coordinates. We have a natural way of inducing coordinates, which is not really enlightening, but it is useful. This is basically the proof. You write it down, do some computations, you arrive at this. Not really enlightening. So, first of all, we have pullbacks. Good. What about Liouville forms? It is just saying that there exist. I mean, I can sort of pin it down. If you have local set with some local generators of the E tangent bundle, so on the base, and you trivialize it and consider the fiber, and then at the fiber V, at the fiber Q, you consider a chart and induce a tangent chart, what this is saying is that it is really similar to fiber bundles. This chart, the union of these charts, is a chart of the induced E tangent bundle on the fiber bundle, the pullback. So what he's saying is, if you have down here like a set of, in fact, this picture sums it up for b-manifolds. For b-manifolds, if you have like a hypersurface, the induced hypersurface is just a preimage by the projection. And in the case of E tangent bundles, you are just considering a certain subclass of vector fields here and saying, well, I will just consider up here all vectors which are projected down to some vector on the E set. Or if you are more comfortable, you can just think about the pullback algebroid. They are the same. Is it somewhat clear? I hope. We can discuss later on if not. So now, Liouville forms. When we define the pullback structure, we can endow the E-cotangent bundle with an E-manifold structure. And this was already done by Eva Miranda, Guillemin, and Ana Rita Pires for the case of b-manifolds on the b-cotangent bundle. And there exists an analog of the Liouville 1 form, which is defined just straightforward. Take the definition for the smooth case and generalize it, and it works the same. And in these coordinates, for instance, we can check that the canonical symplectic form has this expression, and this is kind of interesting because we have a Liouville-like term plus some structure functions on the Lie algebroid structure. And in fact, if you dualize it and project it, you obtain the natural Weinstein Poisson structure on the dual of a Lie algebroid. So this is kind of an intrinsic definition of that structure. So good, we have Liouville forms. Coordinates, the natural coordinates. In this case, you mean? In this case, you are taking, so you would be taking, given that you are considering the pullback, you would be taking open set of U. Here would be like M, you are taking U. And then you are taking the pullback with the E-cotangent bundle. So the fibers are actually some kind of vector space. Like it would be T, P, E, T, P, M dual, kind of. These are the fibers. So if you have a set of vector fields here, a local set of generators, the sensible way to choose coordinates here is by the dual fields. Is the idea. And then apply construction of natural coordinates. Is it clear? Good. So now, interesting part, we can define lifts. And this is where I will be using generically injectiveness of the anchor. Because if we have a diffeomorphism on the base, I have not spoken about the morphisms. Morphisms are morphisms of Lie algebroids because E structures have an E-tangent bundle structure, which is Lie algebroid. You can define morphisms just by restricting Lie algebroid morphisms. But in the case that we have a diffeomorphism in the base, basically there exists just one Lie algebroid morphism between E-tangent bundles, and is the restriction of the natural, like the standard tangent lift. And you can check it because anchor is generically injective. So you are identifying E-tangent and tangent bundles on an open dense subset of M. And just by continuity, you can extend it. So this is kind of tricky. And I will just write it in yellow. And once you have this, you can define cotangent lifts, and you can check that they preserve the Liouville canonical form. So we can define cotangent lifts of group actions. They are Hamiltonian, and everything works as in classical sense. And now there exists an analog of the Mars and Weinstein reduction theorem for Lie algebroids, which was proved by Marrero and other collaborators. In the case of E-manifolds, it is much simpler because given a group action, there exists just one way to lift it. So this theorem is further simplified. And one thing we checked as well is that there exists a shifting trick, or a version of the shifting trick for E-manifolds, which basically takes the standard proof, and as the manifolds are diffeomorphic, all you have to do is check that the E structures are mapped one onto another. And because we have cotangent lifts, everything works. Tangent lifts for diffeomorphisms, everything works. And as a bonus, if you recall the proof of the shifting trick, it is really similar to constructing an adjoint bundle. So we are somewhat getting adjoint bundles as well through the proof of the shifting trick. So good. we're set. Now, for gauge theories and classical theorems, we are defining gauge fields on E-manifolds as certain splittings, and I am sorry, Rui, because I didn't know about MEX, so I have no idea whether this is related, but we are defining E-gauge fields as gene variant splittings of this Atiyah-like sequence. And just a remark, observe that we are identifying the vertical bundle over the principal bundle understood as a smooth manifold with the vertical bundle understood as an E-tangent, as an E-manifold. And this is because we are taking the identification with the anchor. And this is once again a small subtlety. And with this, we basically have this piece of the diagram, because using local normal coordinates, we can show that there exists a version of the splitting lemma for E-manifolds with considering the pullback structure. So now we are interested on the dual splitting, and in particular on the dual of the horizontal lift, which will be the one giving us this map to pullback. And then we can generalize Weinstein's symplectic formulation of Wong's equations in gauge theories. Whenever we have a G principal bundle over a manifold and a Hamiltonian G space, and this Hamiltonian G space already encodes both shifting trick, already contemplates both shifting trick and the associated bundle construction, then technical result, product space is Hamiltonian with moment map, the sum of moment maps, yes, of course. Hypothesis of the reduction theorem are satisfied, and we have an asymplectic manifold. And because of the G invariance of the splitting, the horizontal lift or the dual of the horizontal lift is well-defined in classes of equivalence. We may restrict it and consider the pullback of a Hamiltonian. And now we have what are called Wong's equations of motion. And there is also another version of what would be the minimal coupling procedure, which is an isomorphism with a Sternberg-like space. And this works as well, essentially, because as smooth manifolds, they are diffeomorphic. So just check that they are the E structure is preserved as well, and everything follows for free. And now in the formalism of Poisson manifolds, and now I'm not considering a Q, a G Hamiltonian space Q, just a principal bundle, because this is the setting for Yang-Mills theories, actually. Whenever we have a principal connection, once again, we have that H map, and we can construct this commutative diagram, which we are trivializing down there using the splitting of the sequence. It is commutative, and we can take the pullback of any Hamiltonian on the ecotangent bundle. It defines Wong's equations of motion, and because those spaces are isomorphic as Poisson manifolds, the dynamics generated in each one of them are actually the same, are equivalent. So this also falls within the more general picture of cotangent bundle reduction, which was coined that way, I believe, by Marsden in 1999. And we can also prove using the shifting trick that a reduction, a Marsden-Weinstein reduction by coadjoint orbits also work, and we can recover their results. And so what about applications and the structure of Wong's equations of motion and the minimal coupling? This was motivated by B-Lie groups, which are Lie groups with a closed subgroup of codimension 1. And basically, Bradel, Kissenhofer, and Miranda studied the Poisson formalism for Yang-Mills theories over these manifolds, and this is what motivated all of this research. Here, the basic structure is you just take the quotient map, and this is a b-manifold when you take in the quotient as B structure the identity element. And another physically relevant problems are, for instance, we can compute the general minimal coupling for a b-manifold. Locally, the expression of the minimal coupling is given by coupling the piece, the momenta, canonical momenta, with a connection, with the charges and the connection. And then you basically do some computations and show that the induced Poisson structure is the one we can see down there. And if you contract with an arbitrary Hamiltonian, which has no explicit dependence on the charges, because we are taking the pullback, we have Wong's equations of motion on a b-manifold. So for instance, time derivative of q, if q belongs to the boundary, is 0. Point in the boundary always is constrained to moving on the boundary, but its momentum might not be constant, because it could be coupled with the electromagnetic color charges of the Yang-Mills theory. And the last application I want to explain is when we take the Penrose compactification of a stationary black hole. This is the general solution for Einstein's equations of motion, Einstein's equations for the metric in vacuum on spherical coordinates. This is Schwarzschild's outer solution. And if we take a Penrose compactification, or Penrose-like, because it is actually not conformal, we obtain this normal metric. And interestingly enough, we have the cosecant function, which blows up quadratically at alpha equals pi fourths, I believe, yeah. And so as it blows quadratically, a good candidate for an E structure would be the set of vector fields vanishing quadratically at the boundary. And if we try with these ansatz, we can check that this is an instance of a B2 metric. So if for any reason you are in the street and someone is in a hurry to compute the standard model in a Penrose compactification of a stationary black hole, you can do it if you really want to, and this is the way. So this has been my talk. Here I have some conclusions. Most important one is actually extending this to Lie algebroids, where basically we have we have this, we have this, we have this. This I don't really know. But we don't have lifts. Generally, we have Lie algebroid morphisms, which are kind of generalized lifts. So it would be interesting to check if by considering different Lie algebroid morphisms, which act as generalized lifts, we obtain kind of equivalent dynamics or equivalent formulations for the equations of motion. But this would have to be checked. So in any case, thank you very much for your attention. And, yeah. Yeah, surely. Yeah, here. Actually, because we are having generically injective anchor. There are instances where a singular foliation does not come from an algebroid. For instance, we could have this. So this is a first obstruction. But because the anchor is generically injective, here I have this. I have the construction of the anchor is basically you have a ring equivalence given by Serge-Swann on local sections, right? Yeah, I mean, locally free. I assume if it does not imply it, I'm sorry, I forgot the condition. But I think, yeah, it is locally finitely generated. Yeah, it has to be stronger than any singular foliation, for sure.
functions that vanish at the point, and it's the same thing. That remains constant. So is it the same as a algebroid anchor?
With injective anchor. Anchor, and this is like the key point, anchor is not injective, it is generically injective. Oh, generically. I mean, we have one arrow. Whenever you have this, you have a Lie algebroid with generically injective anchor. And I guess the other way around should work as well, but I haven't really gotten down to the computations. And because proof, it basically uses local expression and Serre-Schwann's theorem for the equivalence. So I expect the other arrow to be true as well. Probably, yeah. Of course, there is like some categorical noise here. Yeah, there is categorical noise here, which you cannot ignore. But I expect it to be that way. Mm-hmm. Mm-hmm.
You have the structure from the base,
Mm-hmm.
and you pull it back to in structure from.
Yeah.
But you can have E structure from P that projects into something from P that is not necessarily the point.
Yeah, probably. But I am taking it as the maximal E structure. Of course, there could be some substructures which project to the same thing, but I am taking it as the maximal structure, which.
Interesting that you don't get the maximum is that, but I'm not sure if it's interesting. But if you get the maximum, you have a P1 and then the
Yeah.
P1 is also a P1. I think it also preserves C. But if you don't take the maximum, you can have something that here is a formulation and relevant, and the prediction is a B1.
Mm-hmm.
I'm not sure if it shows some kind of desingularization.
I really have no idea.
But the other problem when you take not here the maximum, I mean, it may present as a desingularization, but then when you get the Artesian sequence, in the Artesian sequence, you take G, the algebra of the group that you are acting, and if you take something that is not the maximum, this G could be another thing. Could be even
Yeah, probably. Yeah.
that is related to these two groups.
Oh. That is nice. I mean, I haven't really explained it, but the fact that we can identify the vertical bundle on the E-manifold with the vertical bundle on the smooth manifold comes into play in some proofs. When computing explicitly the moment map of the cotangent lift, it comes into play because it becomes the projection onto this component under the trivialization. So it would be interesting to check whether this would remain true or not. But could you ensure that any lifting would give, I mean, if you do not take the maximal one up there, could you ensure that any lifting would be actually an E-map for the above E structure? Surely. Okay. Mm-hmm. Thank you very much for the comment. Yeah, afterwards. Okay, so let's thank Pablo again. Thank you.